Okay, so we have a question here, and we're told that this ladder company makes the ladder that you see right here from 1 foot steel rods arranged to form rows of squares. So we know right away that you have to form squares, right, in this ladder, and that every rod you see is 1 foot long. And here we have a 6 foot example, a 6 foot ladder bridge. We want to make a table and a graph showing how the number of rods in a ladder bridge is related to the length of the bridge. So what do we do? Well, in our table here, I would say that the length of the bridge, right, the length is your independent variable x. And the number of rods here would be your y value. Now, it's not wrong to reverse it. It's not wrong to say, okay, the number of rods is your independent, and the length would then be dependent. That would just mean that you are figuring out how long of a bridge you can make based upon the number of rods you have. We're figuring out the reverse. We're saying, okay, well, if you need to make a bridge of x length, how many rods will you require? So you know how long the bridge should be. This equation and this relationship that we're going to look at will tell you how many rods are required. So let's break that down. Let's say we need a length of 1. How many rods would you need? Well, that's where the idea of the square comes in here. If you look at the grid, let's say this is 1 foot right there, you need the 1, 2, 3, 4 rods to form that square. So I'm assuming, right, you need to have a square. But for 2 feet, you only need another 1, 2, 3 rods. Okay. If you think about the shape of this ladder, right, look what happens with 3 feet. I'll need another 1, 2, 3 rods. Right? Oops, made a mistake there. When I wrote 2 here, the number of rods is not 3. It's 3 more than we had before, so it's 7. Right? It's 7 rods in total. Sorry, we're counting in total here. The 3, so for 3 feet we need 3 more, or 10. For 4 feet, right, 13. You can count that right here. The next 3. For 5 feet, 3 more, and for 6 feet, 3 more. So you can just count up, right? 5 is 16, and 6 is 19. And now we have our table, right? And we have our x and our y, our independent, our dependent. And what you realize is that we can plot these on a graph, where all of the values in the left column are x's in your coordinates, and the y's are the dependent variable, or y is your second y value in each coordinate. So let's graph that. So on our graph, we have an x-axis and a y-axis. And we just define the x-axis as the length, right? So x here is the length of the bridge. And again, we're just doing that to say, okay, look at this graph, and you look at the independent variable, the length, and that will tell you what you need in terms of the number of rods for that length. So the intersection here is 1, but then we just have the length of 1, 2, 3, 4, 5, and 6. Okay, so then on the y-axis, the number of rods that we need goes up from 4, 7, 10, all the way up to 19. Although it looks like I wrote a 17 there. I'll fix that. That's a 19. All right, so here on the y-axis anyway, we also need to include intervals. I'm going to use intervals of, let's say, 2. So we have 2, right, 4, 6, 8, 10, 12, 14, 16, 18, 20. Okay. So I'll write some of these in, 12 and 14. And this is 2, 4, 6. Just to label it. If you're setting this graph up and you have the room, label each point. It'll help you. So now we have our points 1, 4, right? So 1, and this is 4. And then we have 2 and 7, right? This is 6, 2, and 7. 3 and 10, okay. 4 and 13, so here's 12, so 13 and 4, and so forth. And what's nice is, once you form this kind of equation, it looks like it's linear. If you want to predict where the future points will be, connect any 2 points, and all the other dots will fall on the line, right? So I can highlight these points now, right? And I'm estimating here, so this line really helps me. For 5, we have 16, right here. And for 6, where 6 meets the line, that's automatically where? Well, it's right at 19, right? So even with my writing a rough graph right here, we can use the idea that this bridge increasing by a constant rate to recognize the linear portion of it, or the rate of constant change. Now, this is a kind of interesting type of graph because what would it mean to say we need a ladder of 0 feet? How many rods would you need? Well, if we kept the rate of change that we see here that's linear, every time the amount of feet decrease, what happens? Well, we need 3 less rods. So according to this graph, if we had 2 feet, we would need 7 rods. If we had a bridge of 1 foot, we would need 4 rods. But then for a bridge of 0 feet, we would still need 1 rod, right, if I extended this line right here. And the same is true as if I extend past it and in between any points right here. So the question is, does that make sense? Well, I would say no. I would say this is not a typical linear function. And in fact, if I was setting this graph up, I would say do not connect the points in this case, because we don't even know that we can construct a ladder of feet that are not whole feet. Like, I don't know if I can construct a ladder that's 1.5 feet, because on the face of it, it seems like our equation would be y is equal to, all right, mx plus b is our general form. Here the slope is 3 because we need 3 more rods for each foot, and the y-intercept, it seems at least, should be 1, right? Because if we follow the pattern, right, when x is 0, y should be 1. And then we go about it writing it out and we feel happy. But here, right, the problem is, does this make sense when x equals 0? I say no, because why would you need 1 rod if you're building a bridge of 0 feet, right? If you plug 0 into this for x, that would be 0 times 3, which is 0 plus 1, or 1. And I don't think we would need any rods for that bridge. And in between, like let's say you need a bridge of 1.5 feet. Well, that would be, x would be then 1.5 times 3, which is what? Well, 3 times 1 is 3, 3 times a half is 1.5. That's 4.5 plus 1, or 5.5 rods for a 1.5 foot bridge. But if you look at a 1.5 foot bridge, right, it would need 1, 2, 3, 4 rods, and maybe a half foot. So maybe the bridge would close here with a rod, right? And these 2 halves right here, we're making a hole. So that would be 1, 2, 3, 4, 5, 6 rods, really altogether. Not what we're getting here with the equation, which says, again, 1.5 times 3 is 4.5, plus 1 is 5.5. So it doesn't seem that this equation matches the physical model of what we would need in this case, even though it seems to work in the equation. So really, if we were to graph this, all I would do is graph the points we have, right, these points in red. I would not connect them, and I would not extend the line. And as an equation, you could say, yeah, this thing equals y equals 3x plus 1, but let's say that x cannot equal 0, right? And x has to be something that's larger than 0, right? Shouldn't be negative. We don't know what that would mean. And so we're trying to define the interval here efficiently. So if I'm saying x is greater than 0, I don't have to say it doesn't equal 0, because that's already included in being greater than 0. But we also just said, so this is our first conclusion, that we can't have negatives or 0. But we also realized that, hey, if I want a bridge that's 1.5 feet, it doesn't seem to follow this type of equation right here. So what would I do? Well, I'm really saying then that x has to be like a natural number. A natural number is a number that's greater than 0 and whole. So those are the types of numbers that we're plotting here in this type of equation. I'm just writing that in a fancy way. X is an element of the natural numbers. This e means a part of, and this n means natural number. So that seems to be the way that I would deal with this equation. And I think in other videos we might look at how to deal with half increments for this type of model. Alright, thanks.